Okay, guys, so for nuclear chemistry, it seems like the first and the last question have to deal with fission and fusion, so I'm going to treat those like the same question. So basically, you're responsible for being able to identify a fission or a fusion reaction when given like multiple choices, just like you'd have to know if something was synthesis or decomposition. Um, so fusion is taking two light nuclei and combining them to make a heavier one. And if you think about the lightest element on the periodic table, it's hydrogen. Those are always your two reactants. You always are going to have two hydrogens. So they might be isotopes of hydrogen where they don't weigh one. You can have like one that weighs 1 and one that weighs 3. And you're going to take them and you're going to put them together, and you're always going to make a helium atom. Plus, you're going to make lots of energy. So again, the masses of the hydrogens might be different because they are isotopes, but you're always having two hydrogens making helium. And I should put the word combining in there. Okay. And fission is the opposite, and a way to remember that is fission rhymes with division. Fission is taking a heavy nuclei and splitting it into lighter ones. Heavy nucleus into lighter ones. Now, this doesn't happen all by itself. So what a fission reaction is going to look like, either you're going to have a uranium or plutonium. Those are two very heavy elements, plus a neutron. There's always going to be a neutron as a reactant. And what happens is that neutron bombards the uranium or the plutonium nucleus and forces it to split. So you're going to make two lighter elements. Those are going to be two different elements than uranium or plutonium. You're going to make a bunch of neutrons that are going to go on to split more uranium, and you're going to make a bunch of energy. So fission's kind of easy to pick out because it's actually like a very long reaction. So what's good about both of these? You take some mass and you actually lose it and you convert it into lots of energy. So when you think about like the amount of energy a chemical reaction can create, like think about even a firework is a chemical reaction. You see all that heat, all that light. The amount of energy created after a nuclear reaction is going to be a lot greater. So as far as Emma's question goes about like pros and cons, a pro would be that a lot of energy is created. A con would be that these other two elements that you're making, because fission is actually what goes on inside of a nuclear reactor, those other products that you're making besides neutrons and energy, they're also pretty heavy and radioactive. So you can't just like let those go into the atmosphere and have them emitting radiation to the surrounding environment over time. So let's see. Fission. So pro is the energy. Cons, we can say that there's radioactive products, so they have to find a way to like store those and get rid of them. Those products have long half-lives, so they're around for a long time. Okay. And yeah, that's pretty much it for the cons. For fusion, there's one more con. Uranium and plutonium are not easy to get. So it's not like there's like a ton of that stuff just sitting around and you can go get it and, break it in half. All right, fusion. Pro is that it is very clean. So you're making, along with energy, you're making helium, which is fine for the atmosphere. Another pro is that hydrogen is easy to get. So the reactants are just out there in the atmosphere. So it's like, well, why don't we use fusion instead of fission if it's so much better? The big con is that it's too hard to do. If you want to take two nuclei and put them together, think about trying to push together two positive ends of a magnet. As soon as they get close, they start repelling, and you can never get them to touch each other because it requires too much energy. So it's the same thing with fusion. It takes so much energy to push two positive things together that the amount of energy you get out of it is actually not worth it. So if we ever figured that out one day, we would have a lot of problems solved with the energy crisis. But right now it's too hard to do. Okay, Adam's question. Adam, this is a really good question. I actually looked into this a little bit. So I'm going to say that carbon dating is accurate. I'm sure, like everything, there is room for error, but for the most part, as far as I know, this technique is still accepted for dating really old, once living things. What I think is that since the amount of carbon in the atmosphere is changing, the amount of carbon that is original in a living thing when it dies is changing. So if you keep cutting that in half, if your first number that you started with isn't perfectly accurate, then yes, your age would not be perfectly accurate. But I think, I think as far as I know, it's still accepted and used today, and it has to be pretty close and probably the best we can do right now. But that was a really good question. Okay, for organic chemistry, so Rebecca and Raquel, Rebecca, your question is kind of within Raquel, where we're going to review organic reactions. So I'm just going to go through all of them. So the first kind is substitution. Okay. That's where we have an alkane plus a halogen. So I know something is an alkane if the number of C's, the number of H's is double the number of C's plus two more. Or if it gives me an ending to a name, I know it's an alkane if it ends in ane. I know it's a halogen if it's in group 17 on the periodic table. So an example of that would be like Cl2. Okay? So what happens is the halogen wants to get onto the alkane, but alkanes are saturated. They have a lot of H's on them. So the only way to get an halogen onto the alkane is to kick a hydrogen off. Okay? So you would end up with something like this, where I have all H's here, and then here, this bottom H got kicked out and a Cl took its place. Now the other Cl and the other H that are now floating around kind of by themselves, they're going to just bond together and make another compound. Okay, so that's what substitution would look like. Addition is similar to substitution because it has pins in it. This time you're starting with an alkene or an alkyne plus a halogen. So since alkenes and alkynes are unsaturated, you don't have to kick anything off to add something to it. You can just add it. So if it's an alkene, the number of H's will be double. If it's an alkyne, it's 2. Or if they give you the names, enes end in ene and ines end in ine. So that's how you would know. Okay, and again, halogens are group 17. So what happens is when you add the halogen onto the alkene, instead of the double bond staying there, it changes to a single bond to make a group. So now that that middle bond is only a single bond, these two carbons have space on them for something else to add. So my two chlorines or bromines or fluorines, whatever element they are, they can just add to the top. So in addition, there's only one product, where in substitution there are two products. That's like an easy way to tell them apart. Okay, next we have combustion. And combustion is just a organic compound. It could be a compound that's flammable. Okay, these are the things that have to be true every single time. You always have to have an excess amount of oxygen, and any time an organic compound burns with excess oxygen, we always make carbon dioxide and water as products. So everything I underlined will look exactly the same in any combustion reaction. Okay. Fermentation is the process of making alcohol. So you start off with a sugar and you add a catalyst and you make an alcohol and you make carbon dioxide. So how do you know if it's a fermentation reaction? By looking at it. If they give you a drawing, you know an alcohol is made if there's an OH sticking off of that drawing. And you don't have to memorize that, guys. You get that from table R. Or if they give you names, all alcohols end in anol. So if you make something that ends in anol, you know that's an alcohol. That's another thing you don't have to memorize because it's on table R. Okay? All right. Esterification makes an ester. So that's kind of easy to remember. It's in the name. You always start off with some sort of acid and some sort of alcohol. And when you mix the acid and the alcohol together, you make an ester and you make water. Okay, so how do you know if it's an acid? If you look on table R, acids look like this, alcohols look like this. If they don't give you drawings, if they give you names instead, acids end in anoic acid and alcohols end in anol. So it depends on what they give you. How do you know if an ester was made? Esters look like this. They have an O sticking up and an O to the right. If they don't give you pictures and you're looking for a name, esters are named in two parts. So the first name ends in YL and the second names end in anoate. So if anything ends in anoate, you know it's an ester. And you also make water as a byproduct. All right, saponification. It looks like a scary reaction, but all you're responsible for knowing is that it makes soap. And an easy way to remember that, if you look at the first four letters of saponification and you just like reorganize them a little bit, they spell soap. Am I missing any more? Yeah. So the last two, we have addition polymerization and we have condensation polymerization. So how they're the same is that they make polymers. And a polymer is like an extremely long chain. Like we're talking about like taking thousands of little molecules and linking them together to make one giant one. In addition, polymerization, the polymer is the only product. In condensation polymerization, in order to link the little molecules together, you have to make some room on the molecules first, so you take off water. So with the polymer, you also have water as a product. And that's how you would be able to tell the difference between the two. So those are all of your organic reactions. Okay, guys, extra help today is at 10:30 and on Friday is at 9. Okay, so I hope to see you guys there if you need to be.